Now we're going to talk a little bit about torsion. So the main question here, is how does this derivative of my binormal unit vector, how does this behave in relation to t, n, and b? Because we've looked at the derivatives of t and n. So this helps us to think about torsion. So what is torsion? Torsion essentially measures how sharply a curve is twisting out of its plane. So when we consider them together, curvature and torsion, they're really similar to the curvature of a plane curve. So if we define B, the binormal unit vector, as equaling that cross product T cross N, then the torsion, tau, tau being a scalar that we use to represent torsion, that is going to be negative, the derivative of the binormal vector, dotted with the n vector. So the derivation of this is in the text. I don't necessarily think it's important for us to derive that right now, so I'm just going to tell you, hey, this is our torsion definition. Torsion can be positive, negative, or zero, unlike curvature, which is always a positive number. So visualizing the relationship between T, N, and B and the three planes that they form that create this cube. These three planes formed, we've got a rectifying plane, an osculating plane, and a normal plane. So the curvature can be thought as though the rate at which this normal plane is turning as point P moves along this curved path. And then torsion is the way that this osculating plane turns about T as P moves along the curve. And so again, torsion really represents the way the curve is twisting. So I have one other picture that maybe helps you see it a little better. So we'll scroll down here. I'll get this on the screen. I don't want them to be too close. If you consider this P point as a train climbing up a curved track, the rate at which the headlight turns from side to side per unit distance is the curvature of the track. The rate at which the engine tends to twist out of the plane, and that's the plane formed by T and N, that's where the train is like sitting on top of. So the rate at which the engine is twisting out of that plane is the torsion. So again, you've got your train here moving along this path. I'm going to draw a really beautiful train. And it's a train. There you go. That's what trains look like. It's got a pile of coal on the back. So our curvature is being measured right here. The magnitude of the derivative of the tangential vector with respect to distance. And then our torsion is the way that this train begins to lean left or right outside of this plane, the way it's twisting as the, as its position changes along the tracks. So for example, as maybe you're turning and maybe with increased speed, the train might twist a little bit on its axis or axles even, and one of the wheels could start to pull up a little bit. That's kind of where the motion of torsion is. So why is this important to us? Well, we have two formulas. We have a vector formula for computing torsion, which we're going to talk about, a way we can calculate that. And then we also have a vector formula for curvature. I don't know if you remember, but earlier, a few videos back, I said when we were talking about curvature, we learned one method and then we learned a second method. I said, hey, we're going to learn a third method, which is even kind of easier for calculating curvature. So we'll have this third method for curvature first, and then we're going to talk about calculating torsion as well. So here, before we talk more about torsion, we have our vector formula for curvature, which is a little bit easier than the two other methods we've talked about prior. But we couldn't really talk about this because you see there's acceleration in there. We needed to know what acceleration was. So the vector formula for curvature is the magnitude of the velocity vector cross the acceleration vector divided by the magnitude of the velocity vector cubed. This formula calculates curvature differently. We're using a geometric property of the curve, and this is from the velocity and acceleration of any vector representation of the curve, as long as the magnitude of the velocity is not zero. So we can use this for any formula for motion along a curve, no matter how variable the motion may be. Again, as long as the velocity vector is not equal to zero. So we can calculate this geometric property that seems to have nothing to do with the way the curve is parametrically defined. And then here we have our formula for torsion with some new notation we're going to talk about. But tau, the symbol we use to represent torsion, is the determinant of this matrix divided by V cross A magnitude squared. And we can do this as long as V cross A is not equal to zero. So this formula calculates torsion directly from the derivatives of the component functions x, y, and z, being f a function of t, g a function of t, h a function of t, that make up our original vector r. So the first row, these are all first derivatives. These are coming from velocity. The second row, second derivative values, those are coming from acceleration. And the third row comes from essentially the jerk, the third derivative of position. So a little explanation on this dot notation. This is Newton's dot notation for derivatives. And essentially all the dots do are indicate first derivatives, second derivatives, third derivatives. So it's the same as saying, if I say x dot, that's the same as x with the apostrophe, x prime. And think about what that symbol, how we read that. So x dot would be the first derivative of the x component, whereas y double dot would be the second derivative of the y component. And if we had with three dots, we would read that as z triple dot. So all that means is a first derivative, a second derivative, and a third derivative. So we have one more example in this section, and actually even in this chapter of videos, where we're going to find the curvature and torsion for a helix. In this example, we are going to calculate the curvature kappa and the torsion tau for the helix given by this vector r. So r, the vector, is a cosine t I plus a sine t j plus bt times k. And there's an addendum here. We say that a and b are greater than or equal to 0, as well as a squared plus b squared cannot be 0. So first things first, we'll talk about curvature. We have a new formula for curvature. We say that kappa is the magnitude of v cross a divided by the magnitude of v cubed. So what do we need? We need v and a. That's the first and second derivative of r. So my v vector, v of t, remember a and b are positive constants. So the derivative of cosine is negative sine. So I have negative a sine t I plus the derivative of sine is cosine. So I have a cosine t j plus the derivative of bt is just b. All right, and acceleration. So the derivative of sine is cosine, so negative a cosine t I. Derivative of cosine is negative sine, so negative a sine t j. And the derivative of the constant b is 0, so I have 0 k. I'm just going to leave that off. Notation-wise, I was missing that there. All right, so we need to calculate v cross a, find its magnitude, and we also need the magnitude of v. The magnitude of v is the square root of a squared sine squared t, I squared that component, plus a squared cosine squared t plus b squared. If I factor out, if I have a squared times sine squared plus cosine squared t for these first two terms, sine squared times cosine squared is 1 by the Pythagorean identity. So that leaves me with the square root of a squared plus b squared. I'm going to need that magnitude cubed, so the magnitude of v cubed, that's to the 1/2 power. I'll just write this a squared plus b squared to the 3/2 power. All right, the last piece we're going to need to calculate is v cross a. So v cross a. That's going to equal I, j, k. My components for v, negative a sine t. I need to give myself more space here. So say I, j, k. I've got a cosine t and b. And then for a, I have negative a cosine t, negative a sine t, and 0. So in order to calculate this cross product, I'm going to get I times the determinant of a cosine t b negative a sine t 0 minus, remember there's always a minus there, j. And here I've got negative a sine t b negative a cosine t 0 and plus k negative a sine t a cosine t negative a cosine t and negative a sine t. I'm running out of space. I always do that. So cross product, that's going to be 0. So I have I'll have negative minus, so that's going to be a plus there because we're always subtracting. So that'll be AB sine t minus j. Again, I'll get 0 crossing through there. Minus a negative will be positive AB cosine t plus k. Crossing, I'll get positive a squared sine squared minus a negative a squared cosine squared, so plus a squared cosine squared t. Leaving my t's off there. So cleaning up that last term, we see that v cross a is equal to ab sine ti minus ab cosine t j plus, factoring out the a squared, we're just going to get a squared k because sine squared plus cosine squared is equal to 1. Put my vectors back in there to indicate that. So we're working hard here. We're doing work. What is my kappa formula? It's the magnitude of V cross A divided by the magnitude of V cubed, which we have there. So we just need one more thing, which would be the magnitude of V cross A. The magnitude of V cross A, that's going to equal the square root A squared B squared sine squared T plus A squared B squared cosine squared T plus A squared squared, which is A to the fourth. If I look at factoring this, that sine squared and cosine, that's going to give me A squared B squared plus A to the fourth. I can see in that term, I can factor out an A squared. So I've got A squared times B squared plus A squared. And I can take the square root of A squared, it gives me A. So I have A root, I'm just going to commutative property those around, A squared plus B squared. Therefore, my curvature, kappa, is this A times the square root of A squared plus B squared divided by the magnitude of V squared, which we said was A squared plus B squared to the 3/2. Now, if we look at simplifying this, this is a 1/2 power minus a 3/2 power. That's just going to give me a 1. So I'm going to organize that better. A over A squared plus B squared. And if you recall, we did this example in a previous section, a previous video. We got the same curvature for this helix. All right, so one more thing. Let's talk about the torsion here. So considering torsion, I brought in our original R vector, V vector, and A vector that we found in part A. I'm also going to pull in the magnitude. I'll go ahead and write that as well. The magnitude of V cross A, because we need that as well. And we said that was equal to A times the square root of A squared plus B squared. So I know what the magnitude of V cross A is. I'll square that. That's going to give me A squared times A squared plus B squared. Magnitude of V cross A squared gives me A squared times A squared plus B squared. So I know what goes in my denominator. I just need to find the determinant here. And in the determinant, I'm going to put my velocity components, my acceleration components, and then I need my third derivative. Essentially, that's called the jerk. But let's find that third derivative. I'll call that J of t. So the derivative of cosine's negative sign, I have A sine of t. The derivative of sine is negative cosine, so regular cosine, but minus A cosine t j. Must be getting tired because I'm getting lazy. I've left off a lot of my vector symbols. I'm just going to throw all those in there because we all know I, j, and k are vectors. All right, so setting this up, tau, I'm going to find that numerator first. Let's just find that determinant before I write that. So I'm going to have negative A sine of t, A times cosine of t. I don't have space to spare there, and B. Then I have negative A cosine t, A sine of t 0, and A sine of t negative A cosine t 0. So calculating this determinant is going to give me that value in the numerator. And once I have that value in the numerator, I'm going to divide it by V cross A squared, the magnitude of V cross A squared. So let's figure out what my numerator is here. I'm going to have negative a sine t times the determinant a sine t0 negative a cosine t0, and both of those crosses are going to give me 0, so a sine t times 0, that's gone, minus a cosine t, the second one's always a minus, I have negative a cosine t times 0, a sine t times 0. Again, when I calculate that 2 by 2 determinant, I'm going to get 0, and 0 times a cosine t is going to be 0. So I'm really going to only end up with this third term, which is b plus b times the determinant of this 2 by 2 matrix. So I have here plus b, and I'm actually going to write that on the next line, save some space. I've got plus b times negative a cosine t, a sine t, a sine t, negative a cosine t. And since these first two go to 0, I'm going to save myself some space and just pause and rewrite. So just rephrasing what we had, calculating this 3 by 3 determinant, the first two pieces normally are I and j, which we're not using ijk here, but those went to 0, so we're left with this. And simplifying this, I have b times, that would be a squared cosine squared t plus a squared sine squared t, and we should all see here that this is going to turn into a squared. So the determinant of that 3 by 3 matrix is a squared b. Therefore, our tau, once we've done that, it's pretty easy for us to simplify. So we're going to put that a squared b represents this value in the numerator, and in the denominator we have a squared times a squared plus b squared. So tau is equal to a squared b over a squared times a squared plus b squared. Those a squared values go away, and tau is equal to b over a squared plus b squared. This represents the torsion or the twisting. And from this, we can see that the torsion of this helix about this circular cylinder is constant. And in fact, constant curvature and constant torsion characterize a helix among all of the other curves in space. So helices always have a constant curvature and a constant torsion. Whew. All right, so hope you guys hung in there. I know that video got long. As always, email me if you have any questions. And if you're feeling wild, like and subscribe.